Welcome to Simulation and Prototyping. We're picking up with our tutorial using LadyBug and looking at massing and radiation analysis. So what we can see on the screen is basically where we left off with the second part of the tutorial. And now we're going to finish the final third portion of the tutorial. So what we see is the radiation analysis. If we want to make some changes, we can toggle off the analysis. We can turn back on our loft. And so now we can see this without the analysis running. It won't slow us down. And we did put some forethought into the sliders in terms of how we could locate this on the site, front to back. A few problems maybe with the scale of it, as well as a number of other different controls that we have related to where these are located and our ability to manipulate them. So given that, what I want to do is I want to introduce Galapagos. So I'm going to hide the loft and I'm going to turn back on the analysis. Because what's nice is that we can use Galapagos to solve for something related to our analysis. So what is this and what do I mean? So under parameters, embedded within Grasshopper is what's called Galapagos. And what we can do is just click this and pull it down. It's the simplest of components, but it does a really incredible thing. It is a genetic algorithm, and I can explain how that is and how that works and what it does. But we can also do it by kind of looking at it. But we can see two inputs on it. And it also kind of works in the opposite direction than all the things that we've been using so far that move left to right. This moves right to left because what we're doing is we're taking a final result. In this case, I want to take the average and I want to try and reduce the average and minimize the average. We could also try and maximize it, depends on what geography you're in and what climate you're in. But for today, we're going to take the average of our radiation and we're going to try and minimize it. We're going to minimize it by allowing Galapagos to change any of the sliders that we set up before, and it will operate within the range that we have set up for the sliders. So what is a genetic algorithm and how does it work? It basically breeds a population, and the notion of a fitness function is what it's trying to move toward. And so if we are trying to minimize the average, what it's going to do is it's going to randomly try a number of different combinations of those. It will see which ones are closest to arriving at the fitness function. It's going to kill off a certain number of them, randomly populate them, and then breed between them to see what it produces. And every generation that it does this for is a kind of population that allows us to optimize a specific or in a specific direction towards a specific goal. And so let's see how that works. And it's kind of amazingly easy, but there's some incredible things that are going on in the background. So for fitness, let's start with that. And we'll plug in fitness to the result. Oh, not to that one actually, into the average. And you can see we're only allowed here, I think, one maybe I'll test this by holding down Shift. It does actually, no, it only lets us have one fitness function. And so for this, we want our fitness function to be the average. For the genome, these are all of the options that we have to play with this. And so what I'm going to do is I'm going to pull this all the way back over to where our sliders are located. And what we could do is even start with just a couple. Why don't we just plug in the genome, and then I'm going to hold down Shift. Let's start with just the location of this mass on the site. And so in order to initiate this, we double click it. It opens a small dialog box. I usually just have to pull this over. And we want to minimize. We can see the option is either to minimize or maximize. We want to minimize. We don't need to set a time limit, but I think I changed my defaults. My defaults here are probably different than yours, but basically what's happening is that we can minimize or maximize. We have a maximum stagnant population. So the maximum number of generations before the solver stops itself is 50. The population is going to be 50 per generation. We can increase that or we can decrease that, but this seems to work fine. The initial boost is going to give us an initial population of 200. It's going to be 2 times the population that starts there. Maintain is going to specify how many individuals get carried over to the next generation. And so we probably want to increase that, I don't know, maybe 20% that we can maintain. And then inbreeding is 100% is fully incestuous, minus 100% is fully zoophilic. So it seems like this should probably be 0. But it did give me a weird color coding before, so I don't know. We'll see what that does for how it runs. And I didn't change any of these values here. So the next thing that we want to do is we want to go to solvers. And there's 2 different types of solvers. We're going to use the evolutionary solver. Over on the right-hand side, this is going to either show us all the options that it tries, which I like for what we're doing here, only the ones that are better, or not to display any of them. But I want to see every iteration that it tries. And so in this case, it's just going to move it left and right. We can leave those alone, and then I'm going to start from slider setup. So I'll click this. And what it's going to do is it's going to build the first population. And what I may do is just pause the recording or edit a bit from the recording so we can see what this looks like. So I just stopped this after 5 full populations. And given that I'm screen recording, my computer isn't loving this, and so it's taking a while. But what we see in this interface are a few things. One is the approach to the fitness function. And so we can see the range of genomes that are being tried, and we can see them in each population. We can click on each population, and we can see down below the genomes, all genomes, the top 50%, the top 25%, and the top 10%. And so as we look at all of them, what we can see across the second window here are actually the 3, or actually we only have 2. We have 2 genomes. here and here. And so the kind of cross-reference between them and the banding that occurs from that. On the right side, what we see are the entire population within here. And it's hard to see. I don't like the display, but as we click on each of these, we can see their relationship from one of the inputs to the other. And so these are the X and Y components of the location and space. And then these are ranked. Not that we can see them here, but this is the smallest number, just having done this before. And this is the largest number, the furthest away from the fitness function. And so we can reinstate any of these and it will update the file to where that was, only while we have this window open. So from the first population, the best example with the smallest average was, this was the worst that we saw. Should move in a second. This was better. Second population, third population, fourth, fifth, and the sixth population. So if I look at the fifth population, which wasn't completely done when I stopped it, the newest or the highest ranking one there should move again, moved a little bit more. And so while I'm not seeing a huge range between these, like it's not all over the place, but it's randomly selecting them, breeding them. And I think the longer I let this go, what we'll start to see is that trend line will start to move up and we'll start to have a shape like this. And so what it's doing is it's taking the entire population, and then we can see which ones are going forward and which are dying off. What I would recommend is running this, but adding a number of, and adding additional genomes to the genetic algorithm. And so all of the sliders that we had in terms of the non-uniform scaling, the height, the rotation, allow each of those to go in, because what's incredible about the way that this works is that what you'll see here are each of those vertical lines for each input that you have. And so this is an incredible tool that allows you to test a number of your variables specified by the range that you're set for your slider, and then it tries them and it works towards a specific goal. Working toward that specific goal, that fitness function, can be a little bit challenging if you're simply just looking to do a kind of formal analysis of something. If you don't have a quantifiable goal that you're trying to achieve, this may not be the best tool for you. That being said, the ability to test a huge population of these, kill them off, create new populations, kill those off as a way to optimize for something is an incredible tool and is amazingly simple within Rhino. So it's worth playing with this tool as well. And this applies to everything that we've done previously in the semester. But again, I'm trying to introduce new techniques each week, new tools each week when you're ready. And so I hope this helps. Let me know if you have any questions, and I'm looking forward to seeing what you come up with this week. So have fun. So just as a short addendum, I set this Galapagos file to run overnight. It ran about 300 populations, and this was the result. And so at first, when I ran some earlier simulations, I felt that there wasn't enough big changes, but over time, with enough populations running, I'm happy to report that it's pretty incredible in terms of the fitness function, right? Minimizing the radiation on this surface, which is what we set it up to do. Whether or not that's the right thing to do is a different question, but it does seem like it began to learn that kind of self-shading and tucking itself over here on the south side of the site made a lot of sense. And so if we just look at the fixed color plot of the radiation hitting the surface, this is the smallest amount of radiation hitting one of these surfaces that I've seen. And so it's all just to say that letting the simulation run, giving it enough options and giving it time will produce some really nice results. So I'll leave this with you and let me know if you have any questions. Thanks.